Hello, my name is Dan Gamble. I'm with the Construction Engineering Research Laboratory. I'm a research engineer at Searle, which is part of the U.S. Army Corps of Engineers. Today, for this video, I want to introduce the Hydrologic Risk Forecaster, or the HydroRF model. This is a forecasting model for flooding and infrastructure risk on military lands. So HydroRF, the model, is currently undergoing a demonstration and validation through ESTCP, which is the Environmental Security Technology Certification Program, which is within the Department of Defense. So the plan for this channel is to provide updates on this project and on HydroRF as we proceed through the project, and then future videos will also include results from this project. So before we get into the specifics of HydroRF and how and the operational workflow, I want to take a minute to talk about the background. How did this project get underway? Why was HydroRF originally developed? So military installations consist of built infrastructure that must interact with natural riverine systems and mitigate the impacts of floodwaters. So military installations all contain an urbanized area called the cantonment area, but they're just like any other small city. There's usually hotels, a hospital, commercial areas, residential areas, carpools, all kinds of things that are required by the people who live there and work there, and for the support of the military installation. Just like all other urbanized areas, there's roads and bridges, culverts, detention ponds, sewage treatment plants, all kinds of things, just like any other small city. The other part of military installations are more rural and more natural. And these are the areas, the training areas, where soldiers or military personnel go out to train. But just like all other rural areas, there's still roads, bridges, low water crossings, and military-specific infrastructure. And all of this infrastructure, both in the urban area and in the more rural areas of an installation, are usually built in and around river systems. And so they are prone to flooding and the impacts of flooding, just like any rural or urban area that we may live in. Just as an example of how flash flooding has impacted both the infrastructure and the military personnel of military installations over the last 5 or 6 years. There's some examples at the bottom. So 2016, the primary water pumping station at Fort Leonard Wood, Missouri was flooded out during a flash flood event. This resulted in the installation running low on their drinking water, their potable water, until that pumping station was restored to service. In 2016 and 17, military personnel and 1 civilian drowned at Fort Hood, Texas, while attempting to cross flooded low water crossings. And more recently, in 2019, at Offutt Air Force Base in Nebraska, this Air Force Base suffered a major flood event, resulting in millions of dollars of damage. So military installations, just like the civilian world, have access to several different kinds of flood warning systems. So the National Weather Service will provide flash flood warnings, usually at a county-wide or a regional scale, saying that a given county or a given area is under a flash flood watch or a flash flood warning. However, just like for us sitting at home, these warnings are usually pretty vague as far as exactly where the flood is likely to happen, what are the places and the infrastructure that's most at risk for the flash flood event. And they're not always applicable on military installations. The USGS has a network of stream gauges throughout the country that provide very broad flood warnings. And the terminology used for these flood warnings are pretty vague in general, pretty generic. They might have an action stage for a flood event or a minor flood event, but it doesn't always correspond with the nearby infrastructure. So it's hard to know if that warning is applicable to a certain area or a certain type of infrastructure. And there's also a lot of infrastructure on military lands that are more prone to flooding than in the civilian world, such as low water crossings, where by the time you get to the action stage of a flood warning at a stream gauge, it might be too late on the military installation. That infrastructure may already be flooded. There are several military installations that have an extensive network of gauges to provide reactive warning. So what I mean by reactive is they only provide a warning for a flood that is currently happening, not a forecast of that flood. And this can can result in a lag between the threat recognition. So the threat recognition is, oh, look, there's a flood, but the response time to react to that flood, it might be too late because that flood has already started. Also, gauges are usually only applicable within certain areas of a watershed or within a certain reach of a watershed. And there's lots of military installations with little to no gauging stations. So what's the objective of HydroRF in this project? So the purpose of HydroRF is to make available a forecasting model that can provide the Department of Defense with near-term flood hazard assessments and make those hazard assessments relatable to personnel safety and critical infrastructure failure. So the goal is to provide a forecast of potential hazards related to forecasted floods. So within the next 12 to 72 hours, what is the likelihood of a flood event at a specific location and at what time, and how does that flood event, what is the hazard that might generate for a person or for a vehicle or for a specific type of infrastructure? So instead of our current system, such as a gauge station that says, oh, look, a flood is currently happening, how can we forecast the likelihood of a flood? In the same way that a weatherman on TV says 3 days from now, there's a 70% chance of rain. Well, how can we develop a model that can say there's a 70% chance of a flood, of a flash flood at this specific location at this specific time? The goal, the overall goal, is to improve the decision-making capability of a military installation to allow for improved soldier safety and hopefully reduce the costs due to infrastructure failure or the need for on-site warning systems, such as a gauge station. So by giving the military installation a warning, hopefully several days in advance, those installations will be able to take mitigating actions ahead of time to improve personnel safety and also reduce the chances of infrastructure failure or damage. So now we're getting into what is HydroRF. So HydroRF, as you can see here in this workflow, there's several different components or modules to HydroRF and to the workflow. There's the atmospheric module, and then that feeds down into the hydrology and hydraulics modules. And then finally, from the outputs from the hydrology and hydraulics, the hazard assessment is generated, and then the risk is communicated to the shareholders, in this case, the military installation. So for now, let's focus on the atmospheric component or module. And you can see here that there are a whole bunch of different forecasts that are fed into this workflow. So each of these forecasts here represents a model that generates one or more forecast members. So these are, each forecast member is just a prediction of what's going to happen in the future with regards to rainfall in a certain area. So these forecast members come from two primary sources. There's the 557th Weather Wing of the US Air Force and from NOAA. So these are our operational models. And the thing to know about these forecasts, these precipitation forecasts, even if we're just looking 12 to 72 hours into the future, there's a lot of uncertainty. So if we just take one forecast, one prediction of the next 72 hours, chances are pretty good that that forecast might be wrong. We might predict rain where there's not going to be any rain, or we might, in worst case scenario, we might predict no rain where there's going to be a whole lot of rain that results from a flash flood, that results in a flash flood. So one of the ways that we handle this uncertainty is by looking at an ensemble of forecasts. So instead of just looking at one guess, we actually look at many different forecasts. And each of these individual forecasts are fed down through the workflow, through the hydrology and the hydraulics, to help us generate a probabilistic forecast of risk and hazards at specific locations. So the picture here on the top right is an example of what we can achieve once we feed all of these different forecasts down through our hydrology and hydraulics modules. So we take, for example, here on the bottom left, we have 10 different forecast members, and we feed those through our hydrology model. And we end up with 10 different forecasts of what's going to happen with regards to stream flow. So at a specific location over the next week or so, we can say, or we can determine a forecast for each individual member. Since we have 10 different members in this case, we can start to create a probabilistic forecast. So we can look at the average of the forecast, or we can look at the 95th percentile or the 5th percentile to start to understand what's the probability of a flood at a certain area at a certain time. So we can take the output from our hydrology and our hydraulics modules and start to assess the hazard at a certain location for a certain type of infrastructure. So the example that we have here is a low water crossing. You can see on the left-hand side of the top figure, it says depth times velocity. And so at a low water crossing, so an area where a vehicle, like maybe a military vehicle, is going to try to cross through a flooded road, both the flow depth and the flow velocity are important. The reason for this is that we see on the news all the time how people try to drive through a flooded area during a flash flood, and then their car gets stranded. And sometimes the water isn't moving very fast, but it's deep. And so then the car just stalls. Sometimes the flow really isn't very deep at all, but it's moving very quickly. And it really doesn't take very much water to push a car or a truck or even a large military vehicle off of the road and down into deeper water. So by looking at flow velocity and flow depth at the same time, we can assess risk for a certain type of infrastructure, in this case, a low water crossing, though other infrastructure can be assessed differently. But we can see here how all of the different forecast members that we fed into this workflow generate their own individual risk assessment or hazard assessment at this specific location for this specific type of infrastructure. But again, since we have, in this case, we have 10 different forecasts, we can still create our probabilistic assessment of hazard or risk. And this helps us to better communicate to the shareholder, in this case, the military installation or the decision maker, what the confidence of our assessment is. So are we highly confident in this forecast risk assessment, or do we have less confidence? And this is, again, how we get back to what I said originally. How can we do for flash floods like the weatherman does for precipitation, where we say, two days from now, there is a 70% chance of unsafe conditions at a specific low water crossing. And this is a simple version of how that can happen by using probabilistic forecasts. So that concludes my overview for today. Thank you for listening. Like I said originally at the beginning of this video, there will be more videos detailing certain components of our demonstration and validation, and then final results at the end. So thank you.